In a previous video, we looked at the following structures to determine the number of signals that would be present in the NMR for each structure and the integration that we would expect for each peak. In this video, we're going to go through the chemical shift and the multiplicity for each of the signals for each of these molecules. I encourage you to go through and try to make predictions about the chemical shifts and the multiplicities on your own before watching this video. The first structure is 1-bromoethane. We previously determined that there would be two signals in our NMR spectrum. When we look now at the protons in orange, these protons are part of a methyl group. The carbon that they are bonded to is bonded to another carbon. So the chemical shift that we would expect for these protons would be in the alkyl region, so a chemical shift of around 1. When it comes to the multiplicity for these protons, the number of peaks in its signal is going to be equal to the number of protons on the adjacent carbon plus 1. So that means that the adjacent carbon has 2 purple hydrogens, plus 1 tells us that the multiplicity of this peak will be a triplet. For the protons in purple, these protons are bonded to a carbon that's also bonded to an electronegative atom. So we expect the chemical shift for these protons to be somewhere around 3 or 4 in our spectrum. When we look at the multiplicity for these protons, that's going to be determined by the number of protons on the adjacent carbon. So we have 3 orange protons plus 1 tells us that the signal for the purple protons is going to be a quartet. Here is the spectrum for 1-bromoethane. Can you determine which peak belongs to which set of protons? So the protons that we previously identified to be purple are going to be protons A in this example. The protons that we previously identified to be orange are going to be B in this example. So we predicted that the protons in purple would have our highest chemical shift because they were bonded to a carbon that was also bonded to our electronegative bromine. We also predicted that the peak for the purple protons would be a quartet. In our spectrum, at about 3.5, we see a quartet that integrates for 2 protons. So all of that is consistent with the data that we expected for the purple protons. For the orange protons, we predicted that they would have the lowest chemical shift in this spectrum. They would have a chemical shift in our alkyl region around 1. Their signal would have an integration of 3 and a multiplicity of a triplet. For the peak that I've identified as B, we see that integration of 3, the 3 lines in the spectrum so as to indicate that there are 2 protons on the adjacent carbon, and we see that peak in the alkyl region. This peak happens to be a little bit higher in the alkyl region than a typical methyl group, but that's okay. That shift occurs because those protons are not so far from the electronegative bromine. Our proton ranges are approximate, and the exact structure will determine the chemical shift that we see in any particular spectrum. So for this molecule, we previously determined that all of our methyl protons were equivalent, and we would see them all accounted for in one signal. We now also know that we would expect the chemical shift for these protons to be in our alkyl region, so very near 1, and we would expect the multiplicity to be a singlet because in each case we have 3 hydrogens bonded to a carbon whose adjacent carbon has 0 protons. So in the spectrum for this molecule, we see a singlet in the alkyl region right at 1 that will account for all 12 protons in our molecule. Notice that there's no integration provided in this spectrum because the area under this peak doesn't have any other peaks to be compared to. So all protons are accounted for in this one signal. For this molecule is commonly called ethyl acetate. If we were to name this compound according to the rules of IUPAC nomenclature, we would name it as ethyl ethanoate. For this compound, we previously determined that there would be 3 signals in the NMR spectrum. The proton shown in blue will be a signal that integrates for 3 protons. These protons are alpha to a carbonyl, so their chemical shift will be at approximately 2. And the multiplicity for these protons will reflect the fact that the adjacent carbon has 0 protons. For the protons in green, this will be a signal that integrates to 2. This will be a signal that has a chemical shift between about 3 and 4. That's because these protons are bonded to a carbon that's also bonded to an oxygen. The multiplicity of the signal for these protons will be affected by the protons on the adjacent carbon. In this case, that means that the pink protons are going to impact the signal for the green protons. Because there are 3 pink protons on the adjacent carbon, the signal for the green protons is going to be equal to 3 plus 1, or my quartet. For the pink protons, we have a signal that will integrate for 3. The chemical shift for this signal will be in the alkyl region, so very near 1. And the multiplicity will tell us that there are 2 protons on the adjacent carbon, so 2 plus 1 equals 3. So this will be a triplet that occurs around 1 and integrates to 3. Here's the spectrum for the molecule. Can you match the predicted peaks to the actual peaks we see in the spectrum? So if we take our predictions and match them to the actual spectrum, for the blue protons that we identified as A in this spectrum, we expected these protons to be present in a signal that has an integration for 3, and because they're alpha to a carbonyl, we expect the chemical shift to be about 2. So right around 2, we'd see a singlet that integrates for 3, and that's consistent with what we expected for the blue protons that we identified as A. For the green protons that we identify here as B, these are going to be the protons that we expected to have the highest chemical shift because these protons are bonded to a carbon that's also bonded to an electronegative atom. So we said that the chemical shift of these protons would be between about 3 and 4, and in our spectrum we see a quartet that integrates for 2 right at 4. Typically when we have protons bonded to a carbon that's also bonded to an oxygen like what we see here, typically those protons fall very close to 4 in our spectrum. For the pink protons that we identified as C in this structure, we expected these protons to be in the alkyl region. We expected these protons to have a chemical shift of about 1. And when we look at the data, we see that that chemical shift does fall very close to 1. It's a little higher than we might expect for a methyl group that's on a longer alkane chain. Protons that we've identified as C are bonded to a carbon that's bonded to another carbon that's also bonded to an oxygen. So they're 3 bonds away from that electronegative atom, so that's going to help pull that chemical shift to be just a little bit higher than what we might expect for other methyl groups. So overall, this data matches very well with what we would have expected. The spectrum for this molecule provides a lot of really good information to help with understanding your structural analysis. We have good representation for protons alpha to a carbonyl. We have good representation for protons that are bonded to a carbon that's bonded to an electronegative atom. We see multiplicities of singlets, triplets, and quartets. And so there's a lot of really good information, a lot of really good reminders in this spectrum. We will continue our discussion on the predictions about the spectra for the bottom 4 molecules in the next video.